auditorium. So let me move on here. I'm delighted to welcome Dr. William Banholzer, the Executive Vice President and CTO of Dow, of the Dow Chemical Company, to say it fully, as today's speaker in our View from the Top, the first View from the Top of the spring semester. As you know, the View from the Top series gives the college community and the university community a chance to hear from the best of today's business leaders and technology visionaries. Is that me? Okay. I'd like to thank the Berkeley chapters of the American Society of Chemical Engineers, as well as the Society of Asian Scientists and Engineers. And those are the brave volunteers who are, can you raise your hands there, as who've helped put this together. So thank you. And before I introduce Bill Banholzer, I'd invite you to mark your calendars for yet another special event in this View from the Top series coming to the college on Thursday, April 5th. We will celebrate the inaugural Ernest Koo Distinguished Lecture Series with our very special guest, Andy Grove. And please mark your calendars. It's Thursday, April 5th. As you know, Andy Grove is co-founder of Intel, one of the great pioneers of Silicon Valley, a leader in developing the technology and innovation that built not just the Valley, but spurred the entire IT revolution. He's a graduate both of the College of Chemistry, a graduate of engineering, and he's been a professor, he's been an alumnus, he's been a CEO, so anyhow, it's be today, and what he'll talk about, he's a staunch advocate for accelerating the pace on reducing the cost of technology advances in medicine. So please look at the college website for registration information. Okay, so now coming back to today, as many of you know, the emerging field of synthetic biology is taking shape in a big way here at Berkeley. The Berkeley campus and, of course, LBL. You know, Steve Chu taught us to say Berkeley and mean both University of California, Berkeley, and LBL is really quite engaged in an array of research enterprises in synthetic biology and advanced fuels, including our Synthetic Biology Institute, which we launched this year. Here's one of the co-directors here, please, Doug, of our Synthetic Biology Institute. So actually, he's right here, so I want to be sure you recognize you. And Adam is not here, I think. Is that right? Yeah. So these research efforts represent what Berkeley does best, which is to work across several disciplines to tackle issues of a global scale. And they're developing technologies which have a transformative potential in energy, materials, pharmaceuticals, chemicals, food products, national security, and other industries. But really, what we are here to think about and to engage in the conversation that is to follow is really about what are the real possibilities for the future of biofuels and the payoff of these amazing advances in synthetic biology. So we've invited Bill Banholzer to give us sort of a view, as the title says, which is not about the hype, but really both the roadblocks and the concerns about how this technology may shape our dialogue in the future. I know there's a lot of synthetic biology and biofuels zealots in the audience, so I'd encourage you to engage in a friendly repartee at the end of the talk, but in the interim, I hope you enjoy this. So a few words about Bill. He is the part of the executive leadership team at Dow. He works on the corporate strategy for financial performance and resource allocation, and he also told me as we were talking that he also leads their venture arm. And he also said that an special interest in early round investments. He's responsible for this great, huge company, venerable company's global research and development activities, directing an annual budget of over $1 billion. Of course, Dow has done a huge amount for the campus, and the one other activity I'd like to say is the CEO of Dow, supported by Bill and Teresa Kotamchuk, have been pushing the country on this on an agenda for developing road maps for advanced manufacturing. It's the presidential initiative called AMP, Advanced Manufacturing Partnership. And you may recall we had our regional meeting here to support AMP where Teresa spoke in December. So a little bit more about Bill. Prior to joining Dow, he had a long and successful career. He spent 22 years at many parts of GE. In 2002, he was elected to the National Academy of Engineering, and he has served on corporate and academic boards across the country, including currently on the Berkeley College of Chemistry Advisory Board of Rich Matthews here. So we are very, very proud to count you as part of our Berkeley family. Please give a warm welcome to our speaker, Dr. William Banholzer.
Well, thank you for inviting me. It's really an honor to be here. I mean, Berkeley is such a fantastic place, and it's a distinct privilege to be able to talk to you. So I thank you for the invitation. And I'd also say if there's one message I have, that I think you guys all are going to have an amazing career. The education that you're getting prepared for, assuming most of you are engineers, I think is going to be important, because I believe that we have great problems in the world of society, clean energy, water, and engineering is the skills that we need to attract those and attack those vigorously. In fact, there's a great quote from Michener that says, "Scientists dream of doing great things, but engineers actually do them." So as a chemical engineer, I sort of like that one. But what I would say is I'm a little bit disappointed, because I think as engineers, we've let society down. You're trained to close energy and mass balances. You understand thermodynamics, and some of the hype that's out there is actually taking the country down wrong paths and wasting resources. And so what I'm going to give you today is sort of my view of how I think about energy. And you might say, well, what's a chemical guy doing talking about energy? Well, what you would call fuels, we call feedstocks. And we are intimately in touch and synced up with the petrochemical industry. So a lot of the things that apply to fuels apply to us. And in some cases, what they do is going to dramatically affect us. But we all are dealing with commodities, and commodities is a feedstock. And I think that's one of the biggest messages I want to explain today, is that when you think about going into fuels, it is a commodity. It is a private sourced material, not a public good. It's a private source thing. You pay for it. It's in private hands. And it has capital flows that are part of the capital market. So I'm going to try to explain some of the sort of hype that I hear versus what the reality actually is. I also get to run our venture capital arm. So I see a lot of new startups and a lot of new business plans, and it's amazing how many of those business plans forget fundamental engineering. In fact, the first words out of every venture capitalist's mouth is exit strategy. They're not here to make long-term investments. They want to get their money out so they can put it to work. That's not always useful in energy, where you can have time constants that are 10, 20 years. So I think we've got a better job to do. Now, another thing that you need to understand, if you're in a company, you are a financial entity, there's no right that says you have to do research. Research is a privilege that we earn by creating value for our customers. We provide products that they're willing to pay for, which in turn funds new research, so it's a virtuous cycle. But there's three questions that we have to answer. What do people want? What will they pay for? And what can they afford? And to be a successful business, you have to have an affirmative answer to all three of those questions. So for example, we all know what people want. That's self-evident. But what you'll pay for is important. So I want a bunch of apps for my iPhone, but I'll be darned, I'm not going to pay anything for those. I could afford it, but I'm not going to pay that 99 cents. So you need to understand, will they actually part with their money? It requires them to make a value decision of what you're giving them is worth the money. Also, can they afford it? So my son would like a Porsche. He could really pay for a Porsche. He can't afford a Porsche. So we have to have a discrete answer of yes to every one of those questions before we can move forward. Now, I'm in an academic institution, and here I think you have pretty well-defined definitions of success. And this is a 2x2 grid, sort of two axes. You can have huge scientific success, or you can have huge business success, but there are four quadrants to this. So you really want to be there in the upper right. You really want to have great science that creates great businesses. So the transistor, or antibiotics, or man-made diamonds. Look, those are great science that have actually turned into great products. You can also have great businesses that really don't require much science. I mean, that's sort of a devoid quadrant. In fact, cement's about the only thing we could actually come up with. Usually if you don't have good science, usually things sort of go by the wayside. But the important part that goes back again to my previous slide is great science does not mean that it is going to have an impact on society. So buckyballs, Nobel-winning, high-temperature superconductors, Nobel-winning prizes. They've done a ton of prizes in this area, but there's no significant impact on society because of buckyballs. So I have a second question, which is it great science, and why will people pay for it, and why can I make sure that they can afford it? So affordability goes to cost, which is going to be a key theme that goes through this talk. And then, of course, you can have bad science. We all know about the cold fusion, and it's very difficult to say that you're really going to have bad science come of anything. And you can see, look, my view is hydrogen is somewhere in the middle. There's some good science there, but it's just bad business. And then there's a bunch of just things that don't make sense. And that's a whole other talk of how did these guys get venture capital money, but how did they even get DOE money for some of these ideas? It's just a question of back to engineering principles. So the theme here, the question I was asked to address is, how important is biology in solving the world's problems, especially energy? So we have a Dow·s chemicals business, and I would tell you that business's entire future relies on improvements in biology. We have herbicides, insecticides, fungicides that are chemicals that are important, but the true breakthrough and revolution has been increasing crop yields through genetic engineering, introgressing genes into these things to make herbicide-tolerant plants, to try to make drought-resistant plants, to change the output so we can change the oil to have no saturation or low saturation. That is profound. So I don't want anybody to think that I'm not a huge supporter of biological sciences, but I do think we've got a little bit of a balance issue. I don't think it can solve all of the issues that people are trying to apply to, and that's what I'm going to try to spend the rest of the talk on. This is the way I think about it, is we need to stop talking about what's possible and start focusing on what's practical. And practical means capital will flow there. Not, I can get some government money to make a demonstration plant, but will society benefit by taking that knowledge and reducing it through some commercial entity, small business, big business. But again, academic research is not reduced to practice, does not benefit society. And I think most of you are here to try to actually have an impact in society. And if you think back to this possible versus practical, when I grew up, I was expecting by now to be flying around in a jetpack. I mean, this first Super Bowl, they flew around, but they're not practical. And they're not practical for the same reasons that a lot of the biological routes aren't practical, which is the limits of biology and energy density. And so I'm going to talk a lot about energy density because that goes directly to cost, but you've got to carry the fuel, so the jetpack is limited by the strength of my biological knee. And there's only so much I can carry, which means there's only so much I can fly because we only have a given amount of energy density. So even with highly concentrated energy forms, liquid fuels, because remember, we move energy around the world in two ways, by electrons and by chemical bonds. And so chemical bonds by far are the most efficient at storing energy, but even liquid fuels weigh something. So it's just not practical. Now here's a projection of what we think biologically derived fuels are. It's that little black bar, so you can see liquid biofuels there, out to 2035. These aren't my projections. These are what IEA and other EAI and other people have said. And it's 2 or 3%. Now, but if you go to the popular press and look at how much dialogue, press, and funding is going to what is 3% under optimistic assumptions, you sort of wonder, well, why aren't people worrying about the other 97%? So let's just remember, we're now talking about a small part. And so the question is, well, how could I make that bigger? How do I get bio-derived feedstocks for us, bio-derived fuels for most of us, into broader adoption? Well, you've got to also remember, we started, both for fuels and in the chemical industry, from biologically derived feedstocks. And this shows you the biological is that big green biomass. And over time, we have systematically moved away from biofeedstocks, both in the chemical industry and as fuels. And that didn't happen spontaneously. It happened for deliberate reasons, which is it's cheaper to go through fossil fuels. So if we had this trend, you guys say, well, what's different now? Why is this going to all of a sudden be undone? And you could say, well, because we're going to run out, or oil's price is going to go up, or CO2. We've got to do something because we think that CO2 is important. So the question is, well, how are we going to reverse that trend? And are those compelling enough that actually capital is going to redistribute and force us into other options? So here's the biggest problem. Biomass is too reduced, It's too dispersed, it has too low of energy density to compete with fossil fuels. So if you take a refinery, and what I did here is showed BTU per pound, that's the energy density, how much energy do I have per pound of mass, and then I've got what does it cost to actually recover and make that usable. So oil has higher energy density, and for 1 million BTUs, it costs you about $10 of capital. That's $10 you've got to use to build a refinery. If I want to try and make it out of biomass, cellulosics or even corn, that's $30 to $120. So my plant costs me more because my energy isn't as dense, plus the transformations are harder. So the other issue is just scale. We get costs down by making things bigger. You can't do that with biomass scale. You need, because of the lower energy density, plus you need to be the proximity to the feedstock that you're going to harvest, you need 100 ethanol plants to equal one refinery. So you've got a distributed infrastructure that's got to be made from scratch, and you're taking basically organic versus an inorganic source of metals and all these other things. It's not just the biomass. You've got to look at the total resources. How much water do I need? Where's the steel going to come from? There's a lot more than just the biomass to deal with when you look at these costs. Now, the question is, well, what's a fad and what's a future trend? And how do you know the difference? And so I put up a couple up here, and the question is, well, how do we decide? So you clearly remember there was the hydrogen fad. For a while, that was all you heard about. The hydrogen economy was going to take over, and eventually I think people realized how difficult that's going to be. There is no hydrogen mines out there. Hydrogen isn't a source of primary energy, and once people looked at the four very challenging problems, we don't know how to make it without carbon, we don't know how to store it, we don't know how to transport it, we don't know how to make fuel cells cheap enough. I mean, there's just a lot of problems there. So hydrogen sort of died down. I think corn ethanol, most people would agree, went through a big peak, and then most people now are saying, look, but the sort of balances on greenhouse gases and land requirements, and especially since corn is such an intensive crop, it needs fertilizer, it's not as attractive. Biodiesel was around the same time as corn, but then people started realizing what the biodiesel yield is per acre, and that's sort of fallen off because there's a limit. It almost gets to be too small and you can't do it. So the question is, well, what about cellulose, ethanol, and Algae? So I'm going to talk about those two. Now, Dow has always looked for alternatives. In 2002, we spent $8 billion on hydrocarbon and energy. Last couple of years, we spent $22 to $26 billion on hydrocarbons and energy. That's a big number. If we could go back to the 8, we would be happy. And so if anybody's motivated to find alternative sources, it's us. So we have a huge financial incentive to get away from fossil fuels and look at alternative feedstocks. So we looked at this continually for decades. But one of the, these are just a couple examples, which is we looked at PLA, plastic that is derived from biomass, and actually had a joint venture on it, spent a lot more money than I can publicly disclose trying to make that work, and then got out of it. And we got out of it because PLA is a crappy plastic and it's got a cost problem. And so I was really fortunate to work in GE under Jack Welch. And Jack had a very simple, he said, Bill, look, business is easy. Make great products and have the lowest cost. 2 out of 2 is good, 1 out of 2 is okay. And what he didn't say, which was obvious, 0 out of 2 is dumb. And that's what PLA is. It's too expensive and it's a crappy polymer. It doesn't process well, it has a bunch of problems. But you can adapt it and make it work. And actually Cargill and NatureWorks made it work. Now, remember what I said, you guys as consumers, I have to understand what you will pay for. What you want, what you'll pay for, and what you can afford. And so NatureWorks continued with this program, and they actually had, you remember, the Sun Chips bag, which is a bag from polylactic acid. Now, general consensus of marketing data is that people will pay a little bit for green. Most people now, I used to say nobody will pay for green. Most people now, consensus would be, you guys will pay about 5%. You won't pay 15%, but 5% is about what, and it depends on your age and how liberal you are, but that's a general number. But what you won't do is sacrifice quality. That's universal. Even if you'll pay more, you're not going to give up quality. And this is a good example to show you how fickle we all are. That bag worked. The chips didn't fall out. They could print on it. They didn't go stale. And you as consumers rejected it because the bag made too much noise. That's how fickle we are. So when we start talking about trade-offs, you won't trade off So our job is it's an and function. We need sustainable solutions and the same quality and the same cost or lower. Any time you try to trade against one of those and make it an or function, they fail. And that actually had to be pulled off. You can go on YouTube and hear people cracking their bags. But that gives you another example. Now, fuels is the same thing. We don't want any trade-off. So I said most people, 5%-ish of cost is what you'll pay. I'm one of the few I'll actually pay not to use renewable fuels. I have a jet ski, I have a snowmobile, and ethanol is awful. These things sit for a year, and they accumulate water. So I actually pay more at the pump to go to the pump that doesn't have ethanol in it so my jet ski doesn't get wrecked. So you've got to look at all these different, now I'm in California, I probably am an antichrist here saying that, but it's but it just shows you've got to understand consumer psyche because we have to have businesses. We also tried to take and make epichlorohydrin, a very important commodity chemical, from a renewable source, glycerin. We had to kill that program because there wasn't enough glycerin. We would have taken a third of the supply in the world for a world-scale plant, not the world supply of epichlorohydrin, but a world-scale plant, and the price would have gone through the roof, plus we couldn't get enough of it. We tried to take natural oils, soy oil, and make it into polyols for urethane. So the seats that you're sitting on are made out of polyurethane. A component of that is an oil called polyoil and a polyol. And we had to kill that because the cost just didn't work out, and it didn't give a better product. Actually, it gave an inferior product. We could do a lot to clean it up and purify it, but when we did that, the cost ran out, and these, are, again, are commodity chemicals. And then, probably just in January, a couple weeks ago, you saw ADM pull out of its deal with metabolic, saying that they're having problems with PHA. So it's not like people aren't trying this. We've actually executed many programs in the glycerin epi plant. We actually went through final engineering design before we just couldn't get the economics to work. So there's going to be niches, but you've got to recognize there is tried and true companies with good engineering trying these things, and you've got to look at deployment and why aren't these things happening. It's going to come down to economics. So let's talk about algae. Everybody loves algae because the photosynthetic quantum yield is higher than plants, and you can grow it in, they call it pond scum, and this is a typical quote of what people say when you think about algae. Now, I had one of the fellows that works with me was on the NRC recent panel looking at algae as a biofuels, and he was on a blog. Somebody said, we've now figured out how to take and generate all of the transportation fuels that the United States uses from algae. And he asked a simple question, which is, well, how are you going to do this? And their answer literally was, if we divert the Mississippi River and flood and take that amount of area, we can convert the entire transportation fuels to algae-derived fuels. Didn't say it was economical, and you just think, who even thinks of such nonsense of we're going to divert the Mississippi River, let alone the environmental impact and stuff that would have. Here's one of my favorites. Like, again, I told you all these crazy business plans. This one actually is on the web. There's a company out there, LumaGrow, that's saying, we'll sell you LEDs so that you can grow indoor algae ponds. Now, we all know we generate electricity from combustion or nuclear or hydro, but we have, at best, maybe 60% conversion. In a high-efficiency combined gas cycle, 60% of the input energy is converted into electricity. So you already have given up 40% just to make an electron. Then by the time you get that to where you're actually going to have the LED hanging over, and then the LED has pretty good efficiency, and then the algae in their best days get 2 or 3% quantum efficiency, you're throwing away 90% of the light here, and somebody thinks that this is going to, again, they don't close the energy balance. But this is on the web. You can see the press down there, and people are proposing these kind of solutions. A concern for me is if you look at the recent trend, this just shows publications in chemical engineering, I'm a chemical engineer, in reactor design, transport phenomenon, fluid dynamics. These are the fundamental tenets that define what chemical engineering is, and you can see there's some increase, but compare that to the biological publications. It's just gone through the roof. In fact, if you look at, I think the top 50 chemical engineering departments now have 45% of their faculty say they have biological research in their research programs. And this shows you by just some schools. So you can see at Berkeley, 44% do. And my concern is, I think we've lost a little balance. Remember I said biologically derived research is critical for some businesses, but I don't think it's 44%. Our ag business is 15% of our earnings. I'm still worried about the other 85%. So But it doesn't matter because the hype machine goes on. So here's a cover from Science. It actually came from Berkeley, not Berkeley campus, but some of your friends Berkeley down the way, talking about how they've actually showed that since seaweed doesn't have any lignin in it, that they could actually increase the take the plant out of the water, and that they can ferment that and get huge amounts of sugar out of it. And in fact, it made the cover of Science. And here's what they were saying. Look, we have as a country more shore than anybody else. And so the idea that we could harvest seaweed and ferment it is a great source, and they're arguing that they could get 4,000 liters a ton. It was a huge claim. And then you go back and say, look, we've been doing this for a long time. You know, sushi's pretty popular. People have been hauling this stuff in for a long time. It's $400 a ton to be harvested. That's $400 a wet ton. This is 70% water. So this is $800 to $1,200 a ton. That's $30 a gallon ethanol. So you sort of wonder, did anybody just start to look at, when you look at what your input cost is and what you can sell your product for, and when your input cost is an order of magnitude, or at least a factor of 2 bigger than what you're going to sell it for, you're going to go broke pretty fast doing that. Plus, there's an issue of, look, there's this thing called the Redfield ratio, which is the ratio of the nutrients that you need. Plants need not just sunlight and water. They also need phosphorus and nitrogen, and you've got to make sure how are you going to supply that. And in fact, there is one of the biggest things that sort of isn't talked about. We have a lot of agronomists, and we worry a lot about production because there's 2 or 3 interesting facts, which is if the population grows like it is expected to grow, need to produce as much food in the next 40 years as we did in the last 10,000 years combined. So we have to continue to drive up our efficiency at agriculture to feed people. And then another great quote I read in the Wall Street Journal was from the CEO of Nestle, who said, the amount of energy, just BTUs, in energy, transportation fuels, electricity, is 20 times bigger than the amount of energy, BTUs, or kilocalories, whatever units you like, of food that we produce. So when people say that we want to produce 20% of our energy needs from biomass, that means we have to grow 3 times the amount of food that we're growing right now to accomplish that, assuming 100% conversion, and that's before we fed 1 person. So the scale of this is just phenomenal. So how much biomass is available? Not enough. Now, there's different reports that have come out. The NRC just had a report on renewable fuel standards, and they're slightly different, but most would consume or contend that, look, there is a lot of carbon out there. So it's not a question of how much carbon's out there. The question is it economical to be harvested and converted into a usable form? And the recent studies have said, look, for transportation fuels, you could make a dent, but it's not a total transformation, let alone the entire energy. And then the big question is it's not cheap. Most people will say, well, I get it for free. There's a few plants that process wood where you can get stuff for free, but if you're actually trying to get a farmer to give you something, they're not going to do that for free. If they've got to run their tractors and they've got to collect this and it's got to get moved, the general from the National Research Council Renewable Fuels Study said that what people are willing to take, which means I'm a farmer, what you got to pay me to get it, is about $90 a ton, 70 to 110. That's what you're going to have to pay me. And if you look at most biological economic assessments of biologically derived fuels, they're willing to pay 10 to 20. So that's a pretty big gap to close. The other big mistake is people think that biomass is not correlated with the cost of oil. It is correlated. When you've got to run a tractor and you've got to pull it in and you've got to dry it, those have fuel costs. Fertilizers come from fuel. So biomass is not orthogonal to oil costs. They actually has a stronger correlation than people would think. And how much are you willing to pay? In a fuel, maybe 5%. It could be mandated, but for the most part, again, people aren't willing to pay a lot more for something that you just view as something that defines your standard of living, but it's sort of viewed as an essential, and I don't want to pay a lot for it. And then, can you really produce chemicals from biomass? So that was another question. We do it already today, but it's in niche applications. We make spinosad, which is a fermented product. It's an insecticide. It's a naturally occurring insecticide because it's very elegant. So if you need a chiral molecule or very sophisticated chemistry, biology might be the right way to do it. But we also, spinosad is not a commodity. We sell that stuff for a lot of money. And if you're making a drug or something with a very high price, you can afford more costs going in. But we're talking about fuels and feedstocks. Those are defined by commodity prices. So let's go back to the scale thing. A refinery, if you look at the scale and the carbon flux through there, is 100 times bigger than the biggest ethanol plant out there. So the scale thing also gives you a barrier to how long is it going to take to transform if we have the capital and the financial to be able to do it. It's a long journey. So when you see things that say 10 years out, look, 10 years, you're probably still doing reliability on the first plant, let alone having massive change of your infrastructure. People in the venture world that I'm in often say, well, the world's going to be saved by the entrepreneurial startups that California is noted for. And a lot of things that's true, but there's a unique problem when you come to energy. Patient capital doesn't exist. Remember I said the first word out of venture capital's mouth is exit strategy? Well, here's just a comparison of Facebook from when they first hired a few people to when they're sort of self-sustaining, only required $41 million. If you want to build a nuclear plant, it's $5 billion. If you want to build a coal plant, it's $2 billion. If you want to build, MTO stands for methanol to olefins, or EG is ethylene glycol plants. So those are typical, not fuels, but large-scale chemical plants, are $325 million. So the capital that you have to put at risk is much bigger than if you're trying to do an internet startup. So you've got to ask, well, who's going to pay for that, and how long is it going to take? The second thing is the time constant. So when people talk about what we're going to do by 2022, that's 10 years from now. It's over. Nothing's going to change by 2022 of substance. We're building the world's biggest integrated petrochemical plant in Saudi Arabia. It is a $20 billion installation. It's a joint venture between us and Saudi Aramco. It'll come up on 2015. The designs for that were frozen in 2006. So when you think about, I'm going to invent something, well, if you're inventing something, you should talk about impact in 2050, not 2020 or not 2025, because you've got to go through invention, development, demonstration, and deployment. And it's only out here at deployment is when you actually have a big change. So here is one of the fastest chemical transformations, which is a change to single-site catalysis. And it took 12 years, and it cost $150 million. And that then was deployed. But if you look at energy, it's even worse. You look at supercritical coal, it's 50 years, and it's billions of dollars, and we still don't have a lot of supercritical coal plants. So this time constant is a big problem when you talk about energy because of the time frame. And when you build something that's going to last 30 or 40 years, you just don't replicate that till you know that first $1 billion is going to continue to run. You don't build the second billion where you're trying to figure out is the first one reliable. That's why the demonstration processes and programs can take a long time. Now this is probably one of the last charts I'll go through, give you some chance for questions, which goes down to cost. I have 2 or 3 quick charts on cost here. And it's the way I look at the world and harmonize everything, because we talk about different energy units. Gas is dollars per gallon, natural gas is dollars per million BTU, coals is dollar per ton, biomass is dollars per dry ton. So this harmonizes those. So these are the different units that we look at energy for, all harmonized to dollars per million BTU. So the way you look at this is if you say, I'm going to look at crude, and it's at $100-ish a barrel. Well, that says that's about $18 per million BTU. And you can just read these all across, and they'll tell you what our harmonized energy costs. So this is the cost for the energy content of what you're buying. And you can see the whole basis for profitability. Polyethylene is the plastic that your garbage bags are made out of, and it sells for 90 cents a pound. Well, that's $45 a million BTU. That's a high price, and that's just saying if I burn that polyethylene, what is it worth? And then I make that from ethane that we extract from fractionation natural gas. We steam crack that to make ethylene, and you can see ethylene. So we take natural gas, it's $2–3 a million BTU. Ethane is more valuable. It's now about $8 to $9 a million BTU. We take that and we crack it to make ethylene, going up the value chain. And the difference between polyethylene and this input cost is how much profit you can make. So the higher the bar goes, if this is fixed, that's as much profit as you can make. So could we use ethanol? Yeah, you can take ethanol and dehydrate it to make ethylene. So it's another feedstock. In fact, the first way they made ethylene was from dehydration of ethanol. In fact, the first heterogeneous catalysis was dehydration of ethanol in 1797. So a long, long time ago. It's not like this is new science. And so you can look at what corn costs, but here's what ethanol market costs are. At $2, you can read across, that's how much profit you're going to make. So if you look at ethanol, you're going to compete that as a feedstock versus ethane. ethanol is going to get turned into ethylene. And remember I said, it's not good when your feedstock costs you as much as your product. So that would squeeze our profitability. And so if you look at corn, where corn is, or biomass, so let's look at biomass. Biomass actually is still more expensive than natural gas today. And that number can change. This histogram here is over the last 5 years what those prices have done and the market prices have gone through. So biomass at that is pretty expensive. And this is the last chart that I want to go over because it's the one I see most misused. People will show this and say, look at how we're getting excited that now the price of oil has reached the point that cellulosic processes, so cellulosic ethanol, be it pyrolysis or be it enzymatic routes to decomposition, which sort of are, at best cases, nothing's been demonstrated at this, at $120 to $180 a barrel. That's sort of the range that's out there. We are now getting close to price parity, and therefore these routes are now going to be adopted. That is a naive view of capital. Price parity is irrelevant. The price in the market is what people will pay for it. The difference between your production costs and that price is how much profit you make. If I have $100 million to spend, and you say, this is the price, it's going to be $100, $110, I'm going to do every one of these other technologies before I'm going to do this one, because at price parity, I make no money. That's a zero-return product. We don't return zero-return products. And these stand for gas to liquid, taking natural gas and making it liquids, coal to liquids, oil sands, enhanced oil recovery. Every one of these makes more money. The difference between the price and your production cost is how much profit you make. Price parity is irrelevant. So the idea that I get to price parity as some great transformational inflection point is just naive. Capital doesn't flow that way. That doesn't mean you might get some government or somebody to put a demonstration plan in, but it's not the first price. Plus, these prices are for the nth plant, not the first plant. They're saying, as I build 100 of these, I'm going to have a lot lower cost than what I have today. Those numbers go through the roof. We've done extensive modeling on this. What is it going to cost? We are building the world's biggest petrochemical-derived plant in Brazil, where we're going to take sugarcane, make ethanol, make polyethylene out of it. That's a unique case just in Brazil, which if I had more time, I'd go through the economics of. But even that can't compete with natural gas in the Gulf Coast. Well, the reason we're doing that is because Brazil is a closed market. But that plant requires 120,000 hectares. That's about 65% of the area mass of the state of California if I want to produce the world's polyethylene. And polyethylene is a small part of the fuels industry. So it's a real problem when you start looking at land mass and water availability. But I'd argue, look, those are all problems, but the fundamental one is that economics just don't work. And so if somebody can show me a biological route that's going to be economically feasible, I think this could change. But it's just not there yet, and I don't see anybody who's got disruptive technology, because once you start looking at how much water you have to move around or the outside the battery limit costs, these projects just go up, and it goes directly because the material you're buying is too oxidized, and it doesn't look like what you want to make. And that costs a lot of capital and a lot of input costs. So what could change this? So this could all be wrong. Carbon tax. You tell me there's a $100 a ton carbon tax tomorrow, all these economics change. And then capital will flow differently. But we don't even agree on exchange rates. The idea that the world is going to agree on a carbon tax, I can't say we should put our shareholders' money at risk for that right now. So I've got a lot more slides I can talk about, but I want to be respectful of your time. And so with that, I'll stop. And again, it's not maybe the answer you want, but it's my view, and it could be wrong, and I'd be happy to hear what you have to say. Thanks.
Yeah. We have time for questions. The questions are being recorded also, so please ask for a microphone. Roger? Okay, we'll start with. If you feel like introducing yourself also, that'd be great. I mean it for all questions, but certainly.
Boy, am I in trouble. I'm a venture capitalist, and I invested in algae. Our particular solution is oil produced heterotrophically, so without farms. So I have sort of two questions, Bill. One, did your folks look into biofuels being produced with using algae not on a farm? And two, what is your sort of second question? What is your personal view of the prospective consequences of climate change? I agree totally with you that this particular chart would change dramatically with the carbon tax. But what is your personal view as an engineer and a scientist about the concerns or not regarding the consequences of climate change?
Yeah, well, so I'll do the last one first and get the battery over quick. Have you heard the definition of an engineer? You know, an optimist and a pessimist is an old joke. You know, an optimist sees the glass half full, and a pessimist sees it half empty. And an engineer says the glass is twice as big as it needs to be. So that's the way I'm going to answer this, which is, I think I agree with Nate Lewis and all the guys. Look, it's a pretty big experiment to run that you don't get to replete if you screw up the planet. But I'll go back to, we can't solve our national debt. We don't know how to handle health care. We have an infrastructure that's falling apart, and we don't agree on how we're going to fund education. I don't know anybody that says carbon trumps all of that. Maybe here and academically was, but I think the will, remember that, even if the United States has the will to do something about it, I don't think they can afford to do something about it. So, but it could change. Like, you know, Europe might do something, but Europe's kind of bankrupt, right? Europe is on its back. They can't afford the lifestyle they had. And so the idea that we're going to all of a sudden impose a big extra part of the GDP. So I'll give you one quick anecdote, and I walked through the plant bottle. So I can give you lots of anecdotes about what people say they'll do. So Coke and Pepsi would love to replace PET with bio-derived stuff. We make the biggest ethylene glycol plants out there. We know what it's going to cost. We're making the biggest bio-derived plastics plant in the world. Well, they won't pay any more for it. And so we were going through this sort of, well, people won't pay for this. And I gave that example at Cornell where they have a school of business and engineering combined in a class to talk about entrepreneurship. And I walked through this and said, well, this is the cost, what would you do? And finally they got and I said, look, most people do the same thing. They'll pay a little bit more. But then this very smart woman raised her hand and said, Dr. Banholzer, excuse me, I don't think that's the right question. If you're telling me my entire cost is going to go up 5 to 10% to be green, which is, you know, optimistic, I can't afford that. It's not just paying for the PET bottle. If you're telling me my clothes are going to cost more, my car's going to cost more, and she said, the United States does not have the GDP to be able to afford it. Now, we are a rich country if we won't spend the money. So I think it's pragmatically, we're just going to have to learn to adapt, because I just don't think we can change it fast enough. Doesn't mean we won't work at it, but if you say pragmatically, are we going to reach the objectives, I'm questioning. On algae, it comes down to, look, if you're moving algae around and water around, it's just hard. And so, look, a lot of other smart people, we had a program with alginol. It's the same idea. You're going to take the alcohol is going to come off the top. We're not making oils, but the issue there is if you've got to crush, how are you going to get that oil out? If it's spontaneously emitted and you look at what the yield is, how much you've got to put in for nutrients, and then you say, I'm going to sell something for $3 or $4 a gallon. That's what you're up against. And then I'm going to have some kind of, I got to move this around, I got to extract it. And remember, when you build a plant, 50% of your cost is the separation purification parts. So the first thing you learn in chemical engineering, you don't want dilute feedstocks, and you don't want dilute product streams, and you don't want separations. You know, people confuse a mixture of valuable stuff as being valuable. So just because there's something valuable in there, if you've got to pay a lot to get it out, when we steam crack ethane, half the cost is the cryogenic distillation at the back end. So I'm just trying to be pragmatic of, look, where the dollar's going to go and what can we do. Now, we are working on batteries and photovoltaics and things where materials can redefine our footprint, but the costs have got to come down. And so batteries work. Solar photovoltaic work, just too expensive. I think I have a lot better chance of getting photovoltaic efficiency up and cost down, batteries efficiency up and cost down, than I have of redefining photosynthesis and making these economics work, because I don't even, just on a cash cost basis, let me just give you one chart that makes it. This is cash cost. That says somebody gave you a plant for free. You didn't have to spend any money. What's your cost to buy your input and run it? This is ethanol saying, I have no people, I have nothing. This is just saying, if ethanol at market price is converted to ethylene, that's what your cash cost is. This is where the world is. You're not even fourth quartile out here. And this is, you know, I mean, the truth is that's twice that number. So, I mean, that's the length of the putt. And, you know, people want to return. And there's just so much money out there, and you got to figure out how it's going to be dispersed. And so it's a admittedly cynical view, but it's an honest and practical view. Not what I want. That's why I work on other things, but that's what I think. So
Microphone. Oh, somebody else?
Hi, I'm Will Beeson, a grad student with the Energy Biosciences Institute. So just a comment, then a question. So I completely agree with you about hating the hype. I think it's all over the place, and there are many high-profile pieces of work that are very misleading to the greater scientific community. But the difference, I think, with cellulosic fuels is that, and you had it on your previous chart, if you could just put it back up, is that right now there are lots of people making tremendous amounts of money harvesting oil sands. Truck drivers getting $100,000 a year, and you have that higher on your chart than sugarcane-based biofuels. And I think that the long-term trajectory, the reason why I decided to work on it, was that the underlying feedstock cost to produce just lignocellulosic biomass, it's pretty low. It's not that high. You said maybe $70 a ton, depending on, but the trajectory is that it would get better, that it would cost less as scale increased. And so is there some reason you think fundamentally that you can never get value out of that when the feedstock cost is low, the underlying feedstock cost?
Yeah, because one, I disagree the feedstock's going to, we've been cultivating for a hell of a long time. It's not like this is, I don't know what the disruptive technology is to say $70 goes to 20. So, but, oh yeah, but oil sands is lower cost, right? That's my problem. And no one's supposed to stand for it. If I'm up here and only going higher, and oil sands is here and only going lower because I'm going to get scale, you're still 2, 3, 4, 5, 6 times higher than my cost. So I have $1,000 to invest. You put in cellulosics, you're lucky to break even. You're going to have no return on capital. No investor is going to give you your money. And then you say, well, this is going to come down. So the question is, well, how far can it come down? And the thing about deployment is always about what's the next available option and are you financially advantaged to it. So if we can get cellulosic ethanol harvested costs down, you've got a cheaper feedstock. It's not that far off if you go back to this plot. If you really look at what biomass costs, it's not that much different. The problem is $10 a gallon of capital bankrupts you. You can't afford $10 a gallon. And then you say, well, how am I going to get $10 a gallon down? And you say, look, I got to handle liquids. I've got to deal with all the wastewater. I've got to deal, that's why I think pyrolysis has got a way better shot than any chemical route, because you reduce things to simple, but then you say syngas. And you look at what Fischer-Tropsch technology is decades old. We know how to do gas to liquids. Germany did it, South Africa did it because they couldn't get other stuff. Why doesn't the United States do it? It's too expensive. So it's all going to be about, can we figure out the engineering problems that take that cost and get it capital, feedstock, and operating down to where it's now sort of at the lower end of that chart. And if you guys can do that, if you really have a process and a route that actually takes this down, you need an order of magnitude decrease, and you got a lot of things working against you. This doesn't follow 610 scaling laws. You know, remember the size of the refinery? These little fermenters aren't following 6/10. You don't build, 60,000 gallon reactors, so you don't have scale working for you. You've got low energy density always against you. You're trying to make a fuel from a 2-oxidized feedstock, so your carbon unit ratio is going to stink. I just don't know how you fix that. And that's the question. So you could solve feedstock costs, but and then we didn't even talk about land mass uses, because the other big issue is people say, well, I'm going to grow all this stuff, and they show the plot of corn yield, 4x increase in the last 40 years, if you look at bushels per acre. But net primary production, how much actual biomass I generated, hasn't gone up 4x. It's gone up a few percent, and most of that's because of better irrigation and fertilizer, not because we've increased better plants. So can you make improvements? Absolutely. I think we're going to work on it. I just don't think it's ever going to be cost competitive. But the minute people say this is an externality we're going to impose on society, and that we're going to charge $70, $90, $100 a ton of carbon tax, then all of a sudden it's a different playing ground. But right now, I'm just trying to give you sort of what's in the cards today, and we'll see when this election campaign goes up. I bet you it's not going to be the first bullet point of I'm going to deal with greenhouse gases. That's not just going to be what gets you elected today. And so,
I guess, rural development, security of supply, or the infinite resource aspect?
so you ought to talk to DOE. They're real smart. They'll tell you, if you're going to make liquid, that's why they like electrification. And Steve and all these guys tell you better than I can. But if you make gas, it's a fungible thing that'll move around the world. It'll still be set by the global price. And so the fact that you make ethanol, it's still going to be in private hands. And if I can sell it for $5 a gallon in Europe, and you want to pay me, I'm going to sell it in Europe. And that's not a hypothetical thing. There's a great story about the United Kingdom in 2000 had riots. They had strikes because people said the cost of gas is too expensive. The cab drivers and everybody went on strike. At that time, they were getting 3 million barrels a day out of the North Sea, and they were only using 1.5. United Kingdom was energy independent, but it goes to wherever the price is. So, but electricity doesn't move around the world. So electricity that's why the DOE thinks is a better way for energy security. So, but it all comes down to what problem you're trying to solve. If it's energy security, and it all depends on how much GDP do you have and how you want to allocate it. And all I'm trying to do is give you how the capital markets work. So it's not my money, and I have to go get this money from the market. And the first thing they'll ask is, I want to know your IRR, your internal rate of return. I want to know your DCF. These are not hard problems to solve, and the engineering is pretty well worked out. And we're building a $1 billion polyethylene plant from sugarcane in Brazil, and we're only doing it in Brazil. So you got to trust me. I think I know what the economics are. Today, I'd still rather build it and import it from the United States down there, but it's a unique market. So it's the world is going to change, and I think technology is going to evolve. But my advice to you is you can't get so narrow and only work on your one problem. You've got to expand the control volume, just like when you're doing a mass balance, and say, what's everything that needs to happen to make cellulosics work? Do I have enough water? Do I have enough land? Can I get the biomass? Is it going to be affordable? Is the process going to be cheap enough? And you have to solve so many things. I just think it's a long road. I'm glad a lot of other people are working on it. My job is to make sure Dow doesn't spend money where it doesn't get a return, so we're not working on it. Doesn't mean if somebody else invents something, we won't license it and use it, but we're not, I just think that, and hydrogen, we're not doing any hydrogen fuel cell work. We are working on batteries, we are working on photovoltaics, because I think they can address the problem better, they've got more opportunity for improvement, and again, it's a view. I could be wrong, and I don't want to discourage you, and, but I wouldn't give you my capital dollars. So.
I've got two real quick questions. One, have you looked at any technology?
Let's just stick to one question per person, just in the interest of getting more.
Well, the one that I'll talk to you about the other one afterwards. But the question for you is, I look around here. I guess you're from the cold climate and you're practical, and I'm glad that you gave this practical talk. All of the ethanol research around here is looking away from the farms in the Midwest. And if you spend any time on the farms in the Midwest, like I have at Hunting, what comes out the back, the corn stover, is where I assume that we should be putting our effort in, because you only need 20 to 50% to go back into the ground to refertilize it. Otherwise, it just, it decays and goes to waste.
Yep.
And as the last produced study showed, that it's a phenomenal amount of feedstock, but they're not working on it. You ask the people over here at the DOE, they're working on all the Swiss grass and all this other stuff. That's only 10% of the arable land. I don't understand, why can't you go to something practical, have the scientists spend a week or two on some of these farms in the Midwest and understand how this is done? Yeah,
that's a great question. I don't think I'm the person to ask, because we have an agrochemical business. I know a little bit of how corn's made and the economics, and but I can tell you, if you give me that corn stover today, I still wouldn't build a plant, because the plant still costs too much. So that's the problem of, I have all these other options that make me more money. And let me just be candid. The chemical industry is not wealthy. We barely return our cost of capital. Our margins are 10, 15% on good days. In bad days, they can be single digit. So the chemical industry in the United States has only had a renaissance because of natural gas prices going down. So it's not like there's a ton of profit margin that you can afford a little higher cost. We're barely able to continue to earn our cost of capital, which means we can invest in another plant. So the challenge is, we've had a ton of work done on the capital costs, and we work all over the world. Even if you give me free stuff, free corn stover, that plant is still too small scale. I've got distribution issues, and then I've got to build an ethanol dehydration plant, which isn't cheap, and it just doesn't, there's no pipeline. It's just so many problematic problems that I don't think the chemical industry is going to be transformed. And this, look, it could change 5 years from now. 5 years ago, I would have been out here saying the United States is dead because Middle East gas is 75 cents a million BTU. That's why we're building that big plant over there. Well, at $2 or $3, that's rejuvenated the Gulf Coast, and with the United States can now export. However, $3 is probably not sufficient to keep the shale gas drilling, and who knows if that's going to continue with concerns, ecological concerns about fracking and everything. And that's another, but that's, I think, the issue of there isn't as much as you think at a price that you can afford, and even if you have it, the chemical plant still costs too much for something that nobody will pay you for. It's just a tough equation to balance to say, I'll do other things, and so.
Let's get a few other questions in, please.
Hi, I very much appreciate you being here, and I appreciate fielding some of the more difficult questions. So my thought would be two things, actually. Craig Venter, founder of Solera, Human Genome Project, privately funded, he's, of course, been working on various different microbes, including algae, that can be genetically modified to increase their hydrogen output in other forms. I mean, aren't you looking at that? And the other thing is, how do you compare natural gas to your chart here? Because I didn't see any mention of it.
This is transportation fuels. So the way you convert natural gas is cheap on an energy basis, but it's not useful in a car unless you do CNG, which combine compressed natural gas and you put it in the car and burn it. The way on this chart you look at it is gas to liquids, the GTL page. That's where you take natural gas, use Fischer-Tropsch, and make a liquid fuel you could just drop in. So you could do that. The question is that the best source of use of that natural gas? And actually, I got a slide on transportation fuels. If you actually do the math about probably a lot of stuff I was going to talk to you guys about. This is if I have energy source, how I just want to move you around. What's the lowest BTU per mile? And what you can see is if you look at, I'm going to take gasoline down here. And so, look, it's better to burn that gas in an electrical engine and put it in a leaf and drive around. You actually have a lower cost. Although your greenhouse gas emissions are better than here, they're not great. It's better if you actually burn biomass. So, look, the most practical thing that's already done today, take the biomass, burn it, get electricity off. It works. There's no engineering required. And then my argument would be you should put it in a hybrid electric. You shouldn't put it in a full electric because the cost payback isn't going to get done. But if you do that, I mean, and we are doing, in our Dow Corning, I'm on the Dow Corning board of directors, we own half of that. The new electrical generation plant is going to burn biomass. So it's not a big scale plant. So if I was building a 600 or 1.2 gigawatt plant, I couldn't burn enough biomass. But in a small unit, you could do that. Those are things that I think you can do without any engineering that are cost effective and make it work.
Do you have any thoughts, though, about Craig Venter's work and his idea of genetically magnifying the hydrogen output of different microbes? I mean, it's kind of a large project that he's working on. I thought you might have some opinion about that.
Yeah, I think there'll be outstanding scientific publications and dissertations, and I think it's a buckyball. If you could generate hydrogen, first of all, biological systems need to live. And it's just, you can't get around moving that water around, handling that water. You know, one of the analogies I talk about is this. Time you have a biological system, it mainly has got to live, and that puts constraints on it, and you've got to worry about how you manage it, and you've got to worry about the water, and those are all the parasitic losses, and they cost money. And so if you could generate hydrogen, you're still up against photosynthetic quantum efficiency just stinks. You know, it's 2% on a good day. Most of the time, it's really 0.7. So I'm going to take 99% of the light the energy that's coming in, I'm throwing it away. That's why I'd rather photosynthesis is up against photovoltaics, which it's easy to get 10% falling off. I mean, we're at 20%. I mean, we're actually commercializing at 10. You can get to 20. So if somebody could say, I can fundamentally take biological systems and get the photosynthetic quantum yield to 15, 20%, maybe you're starting to get in the game. You still got to worry about the water and everything. And you still got to figure out, once I got the hydrogen, it's not useful. I got to do something with it. A PV panel immediately gives you the most expensive form of energy, electricity, the most useful form of energy, because we can run air conditioners, we can run cars, we can do a lot with it. So if we go back to this slide, and look at, this is what, at 11 cents a kilowatt hour, that beats everything, because electricity is just more valuable. That's why I said if you burn biomass and make the difference between here and here, that's a lot of profit. You can do that, but you have a scale issue. But I got to get photosynthetic yield up to be able to make and even get it, I think, in the ballpark. So that means re-engineering photosynthesis. I think people are working on that. There's things you can do. But it's an order of magnitude kind of movement you got to be even get in the magnitude. That's worries me. Order of magnitude kind of changes, and things that people have been working on for decades requires a disruptive new idea. It could happen, but you should say, even if I have the hydrogen, then what do I do? Because that was only one of the 4 miracles that you need, right? If I have hydrogen free, I got to figure out how to move it around, I got to figure out how to store it, and I got to figure out how to make fuel cells cheap. We don't have those solutions either. So even if you solve A, you got their series. And so, you know, anytime you string miracles together, it's a tougher putt. So, again, I'm happy to
One last
hear what I'm
question.
wrong.
So back there. So make it
Hi, thank you for coming. My question is, you mentioned this a couple of times, but what makes the economics different in Brazil? Specifically, why is it cheaper, you said, is to make in America except for the protectionism?
Okay, so here is what happened in 2008. I don't want to keep you guys too long, but this is the same graph. You read across it. I'm making polyethylene. The price of polyethylene in Brazil is higher. It's a closed market. They didn't have ethane. And they had a stated policy and created infrastructure all around ethanol. They have a climate advantage where you can grow around the year. They have adequate rain, and they have a lot of land. So there's a lot of sugar. It's well established in there. And in 2008, there was a big problem. Ethane got to be 2-3 times what the price is today. It was getting up to what naphtha is, so you can see margins were compressed. And so we started now saying, look, ethanol market prices in Brazil are actually cheaper than what ethane is. So that was in, but you can't take ethanol out, and so that was in Brazil. Now today, here's the reality, that prices are still pretty high, but these things have fallen. Naphtha still is bad, so Europe makes naphtha. It's an oil-derived product, cracks it. You don't want to be in the naphtha cracking business anymore. Those plants are going to go out. They're the high-cost plants. They'll be the ones that shut down. You're going to have to crack natural gas, which is what's happening in the United States. Profit margin is, like I said, here is appreciable. This is what we had to do in Brazil. Is we're actually going to have to be farmers. We're going to have to take the market out of it. We're going to have to take our ethanol because we don't want to buy and be exposed to what is a pretty volatile feedstock. We actually are growing farms right now. It takes you 6 years to grow a sugarcane farm. You have to plant it in stages. And then we sell more at it's 10 to 20% higher price. So in Brazil, people will pay more for polyethylene just because the market's captive and closed. And I can't bring it in from North America. So you can see this cost is cheaper than this. This is still a better plant. But here, I can't get this cost there. So in that market, I can do this. Now, there also is a debate of will we be able to sell it as renewable polyethylene and get a premium for it. And right now, the belief is you'll probably get 5 or 10% premium. That's what most of you will pay to say, I have a green garbage bag. But that's not enough to overcome this delta. And so the issue is, in Brazil, you've got a very advantageous infrastructure. The sugarcane is a better crop. It way beats corn. And that's why if you look at the plot that showed sugarcane ethanol prices are actually pretty competitive. That's why it does work down there. The problem today, though, is actually corn ethanol in the United States is actually cheaper than Brazil market ethanol from sugar, even though the costs are different. So that's another issue of needs, because sugar prices have gone through the roof. People want to eat it. And so sugar's gone up, not because of the fuel value, but because they want to eat it. And so then you get in the food for fuels debate. So you want to
thank you. Yes, I think thank you very much. This concludes the presentation, but I want to make you an honorary Berkeley engineer. It's not exactly a big ticket item, but it's the Berkeley engineer.
Thank you.